Hi guys, we're going to start a new topic that should only last this week, if that, called torque. It's going to deal with how we get things rotating, basically. So, you guys watched a video in yesterday's assignment to get you introduced to it, but I'm going to get into it a little more with some example problems as well. So, to start, general definition of torque, then we'll break it down more specifically. Torque, in order to start or stop the rotation of an object, a torque must be applied. All right. So we really, in this course, don't get too far into rotation other than torque itself. But to rotate an object, that means basically to turn an object that has some kind of axis of rotation. That could be like the hinges on a door. You rotate a door every time you come through. Even the handle on the door, you turn and rotate. It could be a wheel of a vehicle or bicycle rotating around its axle. It could be a wrench using to tighten a nut or bolt, or loosen. But an object to be rotating, it has some kind of axis within it somewhere within the object rotating that's going around it. Rotation is not the same as circular motion. All right, the circular motion, which we covered earlier in the year, an object is following a circular path. Rotation is dealing with an object that is, like it says, rotating about some kind of axis on it or in it. And there are some similarities between circular motion and rotation, like they could kind of come together, but we're only going to worry about torque as applied to rotation right now. All right, so there's really three parts of torque, which is in my next statement. Then I'm going to bring up a simulation to show some of this. Torque just doesn't only depend on the force applied. It also depends on where and how the force is applied. Exactly what that means in a second. Let's just put it this way. If we're talking linear motion like we studied the majority of the year, that just means pushing or pulling things in a straight line for most of the year. To move something in a straight line linearly with no rotation, all that matters is the force you apply. Where you put the force, how you put the force really doesn't matter. So as long as, if you wanted to move a box and you put a force of X amount of newtons on it, where and how isn't really applicable. But when you have something turning involved on an axis with rotation, then just describing it through force is not enough. So I'm going to go to a example here and make this bigger. What this is a balance beam. You can see it's measured the distance away from a central axis. Right there is like a hinge, a central axis, an axle, an axis of rotation, whatever you want to call it. Okay, and these are just some masses I could hang on it. So each one of these masses, they're all in kilograms. There's an unknown one. We're not going to worry about that. But they're all in kilograms, and we should know that if we want its weight in newtons, we could take it times 9.8. Let's just make it approximate. Let's round 9.8 to 10 to make it simple. So if I take, for example, the 2 kilogram mass, its weight would be approximately 2 times 10. So that would be approximately 20 newtons. Okay. I'm going to take the 2 kilogram mass and I'm going to place it on one of these hangers down here. Let's say this one that's 20 centimeters away from the axis of rotation, and it just rotated the system. It tilted it to the right? And no matter where I place this 2 kilogram or 20 Newton mass, it's still 20 Newtons, right? Unless I grab one of the other ones. So I'm going to reset it, and I'm going to place it further out. This is the same mass I just used, and I'm going to place it the furthest out you can. If you notice, this thing tilted or rotated further now, which should really tell us something. In both cases, I applied the same force, the weight of this object. But when I applied that force further out, that's the where part in the definition. I applied it along a further radius away from the axis of rotation. So we're going to call that distance r. Earlier, I put it in a radius of 20 centimeters. Now I put it at a radius of 60, and I got more rotation. That's because I got what's called more leverage from putting it further out. This idea doesn't apply in linear motion, pushing or pulling things straight along an x or y axis. With rotation, it matters. There's another thing that matters too, that I can't really use this simulation to show very well, but I'll explain it. The angle you apply it to. Since these are all hanging masses and hooks, when I place this originally, when I drop this on it right now at this moment, the angle it makes with the arm of this balance beam is 90 degrees. All right. So let's do that. Now that it's tilted, actually, maybe I can use this to show my idea. I'm going to put a second mass on it. Let's say the 4 kilogram one, which is approximately 40 newtons. But now when I hang this one on, since it's already tilted, you'll notice that the angle isn't quite perpendicular. So that's the how part of the definition. Remember, I said in the notes that torque is where and how you apply the force. These masses are applying the force of their own weight to rotate this object. So where means how far away from the axis of rotation, and how means the angle when it contacts. So this isn't quite perpendicular. I don't know what angle it is, but I think we could all agree since it's tilted, that's not going to be a perpendicular force. And it rotates it even more. Now the angles are really not perpendicular. So if I put another one on, then let's say right here, we get more rotation. But there's 3 things that matter. The force, how far away from the axis of rotation, we're going to eventually call that the R value, the radius in meters, and the angle at which the force makes contact with the lever arm where it contacts to provide that force. So hopefully that clarifies those few things that we're going to continually talk about. All right, so now I think we're ready to, just about ready to get into the formula, how those 3 things come into play. But here's just another quick example of, let's imagine if we could see the top view, like top down of a door. You don't normally see a door like that, or imagine that this circle is going to represent the hinge I'm looking down at, and the line is going to represent like the top down view of a door. And this is going to be a swinging door, so there's no handle. It's just you're going to push on it. So without thinking, we do this every day. We see a door, we have to go through it. Where do we push? Even if there wasn't a panel there to push on, just by nature, we would all apply our force right here. It just makes sense because it feels easier to us. The reason why it feels easy to us is because we're getting more leverage by placing this force as far away from the hinge, the circle over there, which is the axis of rotation. So this is that R value I talked about in the simulation. And we also do something without thinking, as long as it's possible. We position our bodies so that force is at 90 degrees or perpendicular, that's a bad perpendicular line, to the arm of the object we're trying to rotate, in this case, the door itself. So those, again, are the 3 things that make torque. We have force and angle involved, where we're applying the force to some kind of arm of the device, and a radius R, which represents the distance away the force is applied from the axis of rotation. Now, sometimes, though, maybe you're trying to rotate something that's maybe you're in a tight spot or can't position yourself accordingly. And maybe you apply your force closer to the axis of rotation, and maybe even at an angle something like this. What ends up happening is it becomes much harder, even if you do one of those two things I just said, to open this door, because you lose what we refer to commonly as leverage. Even if I apply the same exact force that I applied earlier, it now becomes harder to open this door because our value is shorter, and that alone would make it harder. But also, I made something else more difficult. My angle is not perpendicular. When my angle is not perpendicular, I lose leverage as well, and I can't provide as much torque, even if I'm using the same force I was using before. So let's go over now and see the formula, how that all plays out. So the formula, torque, and by the way, that's not a T for torque, that's actually the Greek symbol ta, and it equals F, the force, which I discussed, times R, the distance the force is applied from the axis of rotation, times the sine of the angle between the force and level. Now, why the sine's involved gets into some trigonometry, which for right now we're not going to worry about. I might post another video that derives this a little more thoroughly mathematically, but for now you just need to know that this is a formula that directly defines torque, r sine theta. There's a few other things before we get an example to say about it. Number one, the common units for torque are Newton meters, okay? When we use this formula, we want to make sure our calculator is in degree mode and our angles that we're measuring for theta are in degrees as well. The R should be in meters. If not, we should convert. And the forces always should be in newtons. Now, you might recognize this from a while ago. When we did work energy, we also got Newton meters, especially for work, and we renamed that the joule. And while that's still true, when we find torque, we typically don't rename a Newton meter a joule anymore. I can't give you a great reason why. It's just what's commonly done, or in this case, not done. So when we calculate torque with these values, we'll give like 30 Newton meters, 50 Newton meters, stuff like that. All right, just leave the unit Newton meters and you're fine. We're not going to do any problems with English standard units, but some of you that are more familiar with torque than others, you might recognize foot-pounds as a common English unit for torque. But metric, it's Newton meters, that's what we're going to stick with. Now, there's another thing something to do with this formula, so I rewrote it down here. Remember, I used the term leverage in your diagram on the last page. And the portion I have bracketed here, r sine theta of the overall torque formula, is sometimes referred to capital L, otherwise known as the lever arm length applying where the torque is applied to. But lever arm length is also known as simple leverage, all right? We get more leverage, maximize our leverage two ways: by a larger R radius and or by an angle that's perpendicular. Here's some trig things some of you might remember. Why does the angle perpendicular maximize the leverage? Because sine of 90 degrees, that's perpendicular, is 1, right? The sine of 90 is the value 1. Any angle that is not 90 degrees, the sine of any angle that is not 90 is going to be less than 1, a fraction. So if that is any value other than 90 degrees, a fraction times whatever the R value is, make the leverage lower. You lose leverage when you try to rotate something when a situation does not have a perpendicular angle. So these two values together in this portion of the formula known as the leverage or the lever arm length. It's a simple idea. If you want to maximize your torque, you try to push on a door as far out from the hinges as possible. That's why every door handle is always an